This is lecture 22. Last time we discussed what are the specific concerns of scheduling in operating systems, and I mentioned this 2 by 2 table where here we have a CPU bound process and an IO bound process, and we are trying to compare them in a relative sense. And here is our control variable, which is priority, and here is time slice. And in this relative sense, we said that for a CPU bound process, the priority compared to IO bound processes, all else being equal, is going to be low. And for the IO bound process, the opposite, so it's going to be high. And in the case of time slice, we want to give the CPU bound guy a large time slice, since that's what it needs. And for the IO bound guy, we give a small time slice, since it doesn't need much. And we noted that giving a large time slice to a CPU bound process does not harm these IO bound guys because they are able to preempt, that is, kick out CPU bound processes when they become ready after blocking or sleeping because they have a high priority. All that we need to ensure is that for preemption to occur, we need to make sure that when an IO bound process becomes ready, that we call the scheduler so that we reach the scheduler. And we discussed the main path by which the scheduler of an operating system is reached. Top down, that we called 1, and then bottom up, where we had 2 and 2 prime as examples of how this scheduler that's wedged in between the upper half and the lower half of a modern kernel is reached by the kernel. And one side note here that I mentioned is this table, this qualitative rule, is followed pretty much by all modern operating systems, including the previous Linux scheduler, not the current one, with the caveat that in the previous Linux scheduler, which had a constant overhead, so it was called a constant scheduler or constant time scheduler, this was actually the opposite. That is, these IO bound guys were given a large time slice thinking it wouldn't matter. But of course, it can matter because to know whether a process is CPU bound or IO bound is not for free. It's an estimate, it's a prediction. And when that prediction goes wrong, you don't want to have this IO bound guy having both a high priority and a large time slice, because that would lead to other processes not getting a fair share because this guy will dominate for a long while because it has a large time slice. So and then we discussed how in a high caliber sort of industrial grade operating system called Solaris, it's a uh, variant of Unix, how this guy performs its scheduling, timeshare scheduling, TS scheduling, and we looked at the kernel table and the notion of promotion and demotion of priorities following this very table. So this table is a qualitative table. So this captures a qualitative sense of what is to be done. Qualitative. Uh, in the case of this particular scheduler, it made this table quantitative. So we see exactly in numbers how an actual production scheduler, the one that also produced CS, that is our department, used for many years until uh, recently, that we use to schedule all our processes on our servers. And you could see in this case how simple, straightforward, and in a way also elegant this method was. So what's now remaining is to understand what is the overhead of this nice scheduler. All the other schedulers that are variants of Unix, Windows, they follow the same qualitative table, this sort of directive, but the details, of course, vary from here to there. And this was one such instantiation. So, what's the overhead? What's the cost of Solaris TS scheduling? So here to understand, we can reuse what we discussed earlier, which is we discussed that in a FIFO queue, so it means first in, first out, here we have 3 elements. To maintain this FIFO queue, all we need to have is a pointer to the beginning of the queue, so that's the head pointer, and then we need a tail pointer. And of course, this means first in, first out. So a new guy joins at the end, and the next guy to leave is the guy at the front. And so it doesn't matter how many guys there are, insertion is always at the end, and to extract, we always take out an element from the front. So 2 pointers are enough to implement this FIFO data structure. And when we use FIFO, then we get what we called round-robin scheduling. And round-robin scheduling using FIFO is, of course, constant overhead, because even though there may be 1,000 processes here inside this queue, say that these are all the ready processes, to insert a guy, you just need to follow this tail pointer and add it here. Constant overhead. To then take out the next guy, it's always at the front. It doesn't matter how many guys are in between, and hence the constant overhead property of FIFO queuing, which leads us to round-robin scheduling. So in the case of this Unix Solaris TS scheduling, to understand its overhead, we can reuse this thing here by considering that this guy had 60 priority levels, so from 0 priority till 59 as we saw. So just view there being an array starting at 0, 1, 2, etc., and then 58, 59. So this is an array that has 60 elements. And this is an array of struct, which contains these 2 main pointers. So suppose that at this level 2, so these levels obviously correspond to priorities, since we have this number of priorities in Solaris. So suppose at this priority 2, we have a linked list of 3 elements, so 3 processes that are ready, and all of these 3 processes, so call them P1, P2, P3, all of these 3 guys have the same priority, namely priority 2. That's why they are here waiting at this queue. Of course, there are 2 pointers. Let me show them here back in blue. The one that points to the beginning and the tail pointer that points to the end. So suppose that the CPU is being occupied by some process P7. So here's our CPU, and then the scheduler runs, this guy runs, and it decides to context switch out this process and context switch in some other process. But first, let's focus on the guy being kicked off the CPU, P7. By looking up the table that we discussed last time, suppose P7's priority is demoted to 2. So it had a previous priority now is being kicked out, suppose because it used up all of its time slice, and its new priority is priority 2. And this guy is still ready because it wants to use the CPU. We forcefully kicked it off. So now this guy's new priority is 2, and it has to now join all the other ready processes to compete with them for CPU usage in the future. So how do we put this guy in its right place among all the other ready processes? Well, this guy's new priority is now 2. So we go to this array and use this priority as an index of the array. So this is of course just purely random access. So we go immediately using the priority 2 as an index to this array, immediately enter into this row, and then this is the new guy joining P1, P2, P3. It's a FIFO queue, so the new guy always joins at the very end, and we have a pointer that leads us directly to the tail of the queue. So we do a malloc and then add one more element here for P7. Of course, this is then going to be a null pointer, and then we adjust this pointer now, which was null, to point to this guy. And of course, we have to now update this guy so that, let me show this in black, that it points now to the new last guy here. Of course, the head pointer doesn't need to change. So that's it. That was again constant overhead because we are reusing this property of FIFO queues for round robin. So all the processes at the same priority level, as we said, are scheduled round robin. And then if we have processes at different priority levels, then we follow this invariant that we discussed, that we always want to run a highest priority process first. But for this example, if this guy is 2, we go here, add it at the end. Everything is constant overhead, obviously. Now let's look at the case where this guy is leaving the CPU. So another process, suppose P8 or P11, is now being context switched in. So P11 is being context switched in. But where is P11 located before being context switched in? It must be in one of these rows. Suppose P11's priority is 57. So here is priority 57, and suppose that here we have 1, 2, 3, 4 processes, all of equal priority 5, 7. This guy, since it's been selected, must be the front guy. Then there are 3 more guys. Maybe this guy is P9, this guy is P100, this guy is P6. But by virtue of the fact that this guy is at the front and it's a FIFO queue, we are going to select this guy to DQ. Of course, to pick this guy means that there are no other processes at higher priority. So this must be empty and this must be empty. So 5, 7, this priority must be the highest priority where this list is non-empty. That is, there is at least one process of this priority and there are no processes of higher priority. This is our scheduling invariant, as we called it. So once we have determined that this is the highest priority at which a ready process exists, all that we need to do is take out the front guy. So we have a head pointer that we can use. We don't need to use the tail pointer here. We just use the head pointer, and then we take this guy off, and then we adjust the head pointer to now point to this guy as the first element. And that's what it means to bring in P11 to be the new occupant of the CPU. Of course, this 5 operation is clearly constant overhead because we only need to operate at the front. It doesn't matter that there are here 2000 processes maybe who are already here. It happens to be 3 of them. It's independent of that. That's why it's constant overhead. Now, how about determining that this is the highest priority at which there exists a process? So this is empty, this is empty. Well, all that you need to do is just have a for loop that's going to go from 59 down to 0, stopping at the first priority, at the first index where the list is non-empty. That's what we're doing. So in the worst case, you might then loop 59, 58, 57, 56 all the way down to 0. So hence, how many times do you loop down? 60 times. That's a constant. Whether you have 10 processes inside the system or 2000, the loop count is always 60. It doesn't depend upon how many processes are currently inside the system. Hence, this is constant. All of these 5 operations are constant, and hence the overhead of Solaris TS scheduling that implements this qualitative table is also big O of 1, that is constant time complexity, to be a bit more formal. But we just will call it overhead, constant overhead. So it's a great scheduler because you cannot do any better than constant. It's the very best that we can ever hope to achieve. In the case of Xenu for the ready list, what happened with Xenu? We used a priority queue. And in a priority queue, the simplest method is to sort them and put a process in its right place, which means it was linear overhead, as we discussed earlier. And this is how Xenu's priority queue is implemented. Huge difference between this and between constant. So in practice, we would never implement a linear method, even though it might be simple to do, to implement the scheduling, because we are striving for constant. And if we cannot achieve constant, then the backup plan is logarithmic, as we said. But the nice thing is scheduling can be done in constant time, in constant overhead, and this is one such example. Now let's talk a little bit about Linux's current scheduler. So Linux, let's not use red. So Linux has a new, well, it's not new anymore. It's been several years. So its current scheduler is called CFS, which stands for Completely Fair Scheduler. And as noted, prior to changing to this scheduler, Linux also followed the same table except for that caveat that I mentioned. But rather than fixing that caveat, a completely different way of scheduling was introduced based upon what is called theoretically fair scheduling. That's where the fair comes in. And fair scheduling has not been used in operating systems for a reason, which I will here try to point out. So, in the case of fair scheduling, it's something that's popularly used in networks, so in computer networks, at routers, and such. This is something that is quite popular. And here one uses a more generalized version of fair scheduling called weighted. So weighted fair scheduling or fair scheduler. So WFQ, you will see this thing often. So if you have a WFQ, it means weighted fair queuing. So sometimes you don't say scheduling, you say queuing. They mean the same thing in our context. So what does this mean? Suppose you have three users or three processes or three packet streams. So you are now streaming video. This is one user, this is another user, this is a third user, and you have here a router, a switch through which the packets have to go through, and they have to exit through this wire, through this link. We call it a port because they have to cross, say, from Indianapolis to Chicago, and this is the wire that all the packets here have to go through to reach their own destinations. So when the packets are arriving here, then they are competing for this link that they have to all go through. If it's equal share, we would say, okay, you can share this link with weights 1/3, 1/3, 1/3. That would be equal share. But for this or that reason, you might say, okay, U1, you are more important than these two guys. Why is that so? That's not a question that we are here addressing. That's a policy matter. But suppose it's been decided that U1 should get a bigger share than U2 and U3. Then in this case, we would say, okay, U1, you get half of this resource, this link in this particular case. U2 guys, that is U2 and U3, you guys get a quarter each. Of course, if you then add this up, it again becomes whole, that is 1. So this is a third plus, it's a 1, a half, a quarter, of course, it's back to 1. But obviously this guy gets a larger share. So these are the weights. So if you have some policy where some users or some packets are more important than others, then the weights are the way to reflect those differentiated way, and equal share is a special case. So this is where fair scheduling comes from. It has its roots, but it's not been used in operating systems for the simple reason that operating systems, the main concern is CPU bound and IO bound processes that comprise the real world workload. This is what characterizes OS scheduling compared to other domains where scheduling is done. And to make sense of this constraint that is important in operating systems, we then talked about this 2x2 table as the main guideline by which to implement schedulers. But in Linux, the idea of fair scheduling was imported and it was implemented. And when you implement fair scheduling in the sense of equal share here, what it means is that we are going to monitor for every process that exists, say P1, P2, P3, how much CPU each guy has used up. So this guy has, for example, CPU usage. Let's call the CPU usage maybe C1, C2, C3. Suppose C1 is 2 seconds, C2 is 5 seconds, and C3 is 3 seconds. Well, obviously this guy has gotten the most, this guy next, this guy the least. So now if the goal is for them, for P1, P2, P3, to eventually get about equal share, and now the scheduler has to decide, which do I now run? This guy, this guy, this guy. Obviously, you're going to select the guy with the smallest CPU usage. So you're going to apply a minimum operation on this and pick in this case who has the smallest CPU usage, which turns out to be P1, and that's the guy that you select. So this is the main rule that you would apply to try to implement a form of equal share scheduling in the sense of fair scheduling. So you would monitor CPU usage, which is needed anyhow for accounting and other purposes, but then you would try to use that as the priority of a process to pick who to run next. So the larger the CPU usage, the lower its priority. The smaller the CPU usage, the higher its priority. So here the values go in the opposite direction of how important they are when the scheduler picks them for scheduling. So a minimum operation, so a minimum operator has to be applied to make this work. Now, in all of this, these issues of CPU bound, the trade-offs, and increasing responsiveness of this IO bound guys is not the starting point. It's the simplistic idea of let's make them equal, share, fair. But the reason why this is not so well suited for OS is because this doesn't come into play explicitly. Moreover, uh, suppose that you have this scenario. So here is a scenario A where suppose this is time, and suppose we have two CPU bound guys, and here in the past a process say P5 was created and it ran, suppose, so this is a quite extreme example, for 1 hour. So this is a long running guy. And then a new guy comes along, this is P6. Now P5 and P6 are competing. But obviously this guy is just born, so it has C6 being 0. It has yet received no time. This guy C5 is 1 hour. It's an eternity in terms of CPU time. So who does the scheduler pick now to run? It would pick P6 because it has 0 time versus this guy which has a lot of time. And then it would take 1 full hour of this guy just running for this guy to catch up to this guy to make them equal share. This of course is nonsensical because this is purely due to the fact that this guy was created much earlier. So that should not be the way that the making equal share is applied. So in this particular case, when the new guy comes along, we are not going to give it a 0 time, we are going to give it a fake time. It's called virtual time. So we have to now fake it and give it some time that's much closer to this time. Maybe we give it this time and then do round robin. But we cannot use the simplistic 0 and this to make work because it would immediately break down in terms of what we are able to or what we are going to achieve in the real world. Secondly, suppose that we have a scenario B where again this is time, and here is a process that is CPU bound. Suppose here is process 7, this guy is CPU bound, and suppose here is a process P8 that is IO bound. So this guy is CPU bound, this guy is IO bound. So P7 ran for a while, P8 now is going to wake up. But suppose P7 ran for 20 minutes. It could be even 1 hour. P8 ran earlier, but it used up a teeny time slice and then it went to sleep. It blocked. Suppose here it slept for 20 minutes. It wakes up. This guy has at least 20 minutes to its credit, which lowers its priority by a whole lot. This guy has, suppose, received in total 2 seconds. That's all that it got since it was created. Obviously, this guy has a much smaller CPU usage than this guy. So this has a much higher priority than this guy. And so P8 would rightly preempt P7 and get to run next when it wakes up. That's all very good. But P8, who was deemed to be IO bound, maybe it was IO bound earlier, but now it behaves as a CPU bound process, which means it keeps running and running and running at much higher priority than P7 because it has used up only 2 seconds and the CPU usage is the priority, smaller CPU usage meaning higher priority. So again, P8 would dominate P7 for a long time before these numbers will become similar, before they balance out. And that again is not acceptable because it would starve P7 for too long a time. So in practice, this is again not what's done. When P8 wakes up, it's again given not its actual CPU usage, but a fake time, a virtual time as its time, so that this doesn't happen. So all of these heuristics, these ad hoc ways of resolving the issues that arise in operating systems between the conflict of CPU versus IO bound guys have to be dragged into fair scheduling when we apply it to fair scheduling. That to a large extent defeats why we use fair scheduling. Fair scheduling is super nice and elegant in these settings where we don't have to deal with all of these special traits of operating systems workloads. So for that reason, fair scheduling was not viewed or was not a good method to employ for process scheduling because of all these complications. If I were to ask you to implement in Lab 3 Linux's CFS, which I sometimes ask students to do, then I would go into this in a bit more detail, but here I'm leaving it at this conceptual level. Moreover, there's one more drawback of applying fair scheduling in this way to operating system scheduling, and that has to do with the overhead. So all of these issues that I mentioned introduce complications. So complication A, complication B. So this fair scheduling becomes much more messy now. You might as well just do everything from the get-go based upon the table, which is what all schedulers, all main production schedulers, except the newer Linux scheduler does. But what about the overhead? What about the overhead of fair scheduling? In fair scheduling, CPU usage is the priority. Small CPU usage means high priority. High CPU usage means low priority. And the CPU usage is now not the real CPU usage, but a fake CPU usage, a virtual CPU usage. For the reasons that I mentioned, for consideration of these practical issues. Okay, but whether fake or real, it's the CPU usage that is the criterion by which a process is picked to run next. So we need to pick the minimum of these values. But when you have CPU usage, again, fake or real, it's over a wide range of numbers from 0 until some high number. If you're using, for example, 32 bits to keep track of this usage, it would be unsigned to the 32, of course, minus 1 because we start from 0. It's a huge number. It is a constant, but of course, we don't view this thing as a constant. It's a huge number. So you need to apply a minimum operation where every process can have a CPU usage in this very wide range in general. So if you were to do what Zeno does, which is implement a priority queue, this would mean that you would do linear, and that would certainly not be acceptable. So the next best thing is you achieve logarithmic overhead by implementing a balanced tree structure. And you learned about such data structures in the data structures course, where the idea is you have n elements with a key value like their priority, and you want to store them, and you want to achieve, you want to support two operations, insert NQ and extract DQ, and you want these operations to be reasonable, meaning you want them to be log n, where n is the number of elements. In our case, n is the number of processes. Of course, we're interested in the ready processes, and of course, in general, all processes can be ready, so therefore, just processes is enough to say. And then when we have such a balanced tree structure, of which there are different specific types of structures, you will have heard about heaps, then in this heap-based structure, you can create a tree whose depth is log n. So when you're going to insert, you have to do a tree traversal, but you don't have to go further than log n. Same thing when you have to extract. So hence the logarithmic overhead of that. So when you have a range of priority values, because you are making CPU usage, which can range over a large range, to be your priority, then picking the minimum is what you need to do, and picking the minimum incurs, in the best possible case, logarithmic overhead. So not only do you have to complicate fair scheduling because of all the issues that I mentioned, plus more, in addition, you are paying a logarithmic overhead to make this work. Whereas, as we just saw, the OS specific schedulers, they are constant overhead. Because in these schedulers, you have only 60 priorities in Solaris to worry about. In Windows, 16 priorities suffice. In Windows, there are more priorities than 16, but those are for other classes like real-time processes. For the processes that Windows schedules that correspond to what we are talking about, is timeshare processes, 16 suffices, and Windows works perfectly fine for these things. So you don't even need 60, you can do with 16. You can probably do with fewer than that. In your current lab, you are in essence doing it with two priority levels, one for CPU bound guys and one for IO bound guys. And you will find that, yeah, this will work fine too for the most part. So what all the experience of running real world systems has taught people is that to achieve reasonable scheduling that achieves a nice compromise between CPU bound and IO bound processes, you don't need that many priorities. Just in the teens, that's enough to achieve very good performance. If you switch to fair scheduling, you're giving up on this for no reason. Why use CPU usage as your basis to perform scheduling, which means that you have a wide range of values from which you have to calculate the minimum of, which in the best case leads to this logarithmic overhead. When it turns out that using just a few constant number of priorities, you can achieve very good compromise and very efficient scheduling, constant overhead scheduling that balances CPU bound guys and IO bound guys. So there's nothing wrong in having a logarithmic scheduler because, as I mentioned, in practice, log cost is very close to constant in practice. But if you can achieve constant, go for constant. Don't go for logarithmic, even though in practice it may be very close. Anyhow, since you're not implementing Linux CFS for the lab, I leave that discussion here. Sometimes I ask students to implement the Solaris TS scheduler, in which case the two columns that I did not discuss come into play. There's no need for that at this junction. So understand that in the context of operating systems, having a compromise being reached between CPU and I/O bound processes, which characterize the workload under overscheduling, is the primary concern, and giving higher responsiveness to these guys that voluntarily give up CPU is our goal to achieve better compromise and fairness than would be achievable by using round robin alone, as we discussed. So that concludes our discussion of scheduling. Now let's go back to our slides and wrap those things up here. So a few more items here in the slides: process suspension and resumption. The main thing is not about this part. This is fairly straightforward. You are doing now much more in-depth stuff with Xenu. But here is one slide that, of course, you're going to switch your state when you suspend or when you unsuspend. That is resume a process, which you did from the very get-go in Lab 1. But the key thing is this thing. A note about system calls in Xenu. So you have already noticed, because you have been modifying system calls for Xenu in the labs already, that Xenu system calls follow a particular structure. Namely, so here is a system call in Xenu, and so here's some system call, for example, change prior that you're familiar with two arguments, or resume, whatever the case is. The thing is that when we enter the system call in Xenu, we first disable interrupts. That's the first order of business. Then we do our stuff, and then before we return, we again restore interrupts. So here the question is, why not just do CLI and STI? Just two instructions and just be done with. And in a earlier version, this is exactly what was done. So then what is this business with calling disable and then saving a mask and then using the mask to restore interrupts? What this is about is a more improved programming practice. It's not essential. It is just something that highlights a good way of doing programming. So what is that about? What we mean here is, let's go back to the slides. So what we mean here is, suppose that two people, Alice and Bob, are doing kernel programming. So here's Alice and here's Bob. And suppose now Alice is responsible for coding some kernel function A, B, C. So that's Alice's responsibility. So she codes this function. And this is a kernel function. It's an internal kernel function. Internal kernel function. And this function calls another internal kernel function, def. So this code here is supposed to be, so this piece of function is supposed to be coded by Alice. So that's Alice's responsibility. But this function def, its code, is supposed to be coded by Bob. So this is Bob's responsibility. So let me show this in green. So Bob is supposed to code this guy. And we will see soon enough that in modern operating systems, by default, when you make a trap system call, of course in Xeno you change some of them to be trap system calls, but that's about it. In Linux, Windows, all system calls, of course, must be trap. So, and they are switched from user mode to kernel mode, etc. But the other thing is that in modern operating systems, you don't disable interrupts unless you absolutely have no choice. And we will discuss why that's the case soon. But the point being, this internal kernel function may be running with interrupts disabled or enabled. We don't know because this function is called by some other internal kernel function. So here's the thing. Alice codes this function, Bob codes this function. And suppose Bob needs to perform interrupt disabling here to carry out Bob's work, because to not interrupt disable may not lead to a satisfactory solution. So Bob wants to perform interrupt disabling. So Bob might say CLI, I'm just writing the assembly code mixed in with this, and then after Bob's done, Bob is going to do STI. So here disable interrupts directly and then re-enable interrupts. So in our x86 architecture, it would mean that the IF flag, the IF bit of the eFlags register is here set to 0, and then here it's restored back to 1. But this way of doing it would be correct if Alice had not done the same. So if Alice, before calling DEF, if Alice had kept IF, so if Alice had kept IF to be 1 before calling DEF, so interrupts were still enabled, then DEF disabling interrupts and then here again re-enabling interrupts would, after DEF, set IF back to 1, and of course everything's good to go. But suppose that Alice's code also does CLI here, because Alice needs interrupts to be disabled for her own code. And then she calls DEF. And then she has more stuff to do, and at the end, before ABC returns to its caller, she then re-enables interrupts. That's her code. But now DEF, written by someone else, by Bob, is also doing CLI and then STI. So what's happening here? CLI sets IF to 0. DEF is called. CLI. No need to call CLI because IF is already 0, but Bob calls it anyhow. Bob does his thing and then calls and then executes STI, which sets IF to 1. But here IF should still be 0. It shouldn't be 1. So the fact that Bob and Alice are not coordinating well, or the entire code is written by Bob and Bob is just not being careful enough and does CLI STI here when it's bracketed by another CLI and STI when a function call is made. So whether it's done by 2 people or by 1 person who is not being sufficiently careful, if you are directly executing CLI and STI because it's fast and efficient, it can more easily lead to this type of bugs. So to prevent that, what you can do is you can now use a mask notion so that instead of, in this case, let's see here, instead of executing CLI, you remember what this IF bit is. If it's 0, you remember, oh, it was 0. And then when you're done, you put it back to what it was. You don't just directly set it to 1. If it was 0 before you did something, you then put it back to 0. If it was 1, you put it back to 1. And if you follow this rule, then this contradiction cannot occur. So this is the main benefit of using, in this example here, is the main benefit of using disable, saving the mask, and then using the mask to restore, in our case, the IF bit to its previous state vis-a-vis just executing CLI and STI directly. In our architecture, if you are programming carefully, which you definitely should when you're doing kernel programming, this is not needed, but it's sound programming practice which allows you to try to avoid these mistakes from happening. So this is one thing here to emphasize. The other thing to note is in system calls, you have to be very careful about checking that the arguments being passed are valid. So this is not just any function call, it's a system call where you are trapping from user mode to kernel mode in general. Not in Xeno, obviously, but in general. So you cannot have the user send arguments or pass arguments that are not expected by the function. So they are perhaps sort of out of range, too large, too small, maybe the type is not just right, whatever the case is, which then possibly can cause this function to misbehave. So checking that the arguments being passed are valid is critical to coding system calls. It's much more rigorous, and it has to be much more rigorous than coding some user function, because the damage of not doing so can be, of course, significant and break down isolation protection. So a lot of checking instructions go into performing argument checking. So these are the things here to just keep in mind. In Xeno, the system calls uh, always by default disable interrupts, and then they're going to restore interrupts, and that's it. We could use here CLI, STI, perfectly fine, but why are we using this mask-based way? It's a more general and a more robust software engineering practice. That's the thing here to keep in mind. And in terms of the system call suspend, so we pass a PID, we disable interrupts, we are calling these macros to make sure that the PID being passed is sound. So this macro checks that it's not negative, that it's not bigger than some value that's allowed, or that it's the null process, because the null process should never be allowed to be suspended, because it must always be ready, so that if there are no other ready processes, then the null process is going to run. And then we go into the code and then we do the actual checking. Very simple things to do. And then there's the code for resume, which you already took a look at. And here is the internal kernel function ready that we saw. So we want to make a process ready. We pass the PID. Again, while here we are checking whether the PID is correct or not. This is not a system call, it's an internal kernel function. So whether you check it here or whether you check it before you call PID, that's purely an option. And then we get the address of this guy's process table entry, we set the state to ready, then we insert this guy into the ready list, which in Xeno is a priority queue, which of course in general in Xeno takes linear overhead, which is what we just discussed. And then we call the scheduler to determine who to run next. That's all that this guy is. And then the code for resume that you partly looked at when you're doing lab 1. So very, very simple, very few lines of code, which is really the biggest or one of the biggest benefits of Xenu, where you're able to get to see pretty much all of its code and understand what's going on without any mysteries. So that concludes the discussion of uh, scheduling and some tidbits about process resumption and the structure of Xenu system calls. The next topic is still going to be under process management, where we are going to make processes talk to each other. So that's called inter-process communication, and that we are going to make them coordinate. So that's called process synchronization. But before doing that, let me conclude today's discussion here with one remark that I noted earlier, which is useful now to note, namely, we first discussed isolation protection, and now we discussed scheduling and context switching. Context switching plus scheduling. They always, of course, go together, these two guys. So, how are they related? Now that we have this and this in place, what has this given us? What has context switching scheduling given us? It has made it possible to give the illusion to every running program, so a process, that the process owns, so each process is given the illusion that it owns, in our case, the CPU, owns CPU. Obviously, that's not true because the CPU is being shared by many processes that coexist, P1, P2, etc. But we are giving the illusion through software by implementing this over this substrate that a process, this software that's running, actually owns the CPU that in reality is being shared by all of these guys. This is not a dedicated resource for one process, it's a shared resource. But we're able to give every process the illusion that they own it, because by context switching from here to there, we're able to set things back to where they were, so that when P2 runs, then it continues where it left off. Same for P1. So it's a case of illusion or virtualization. It's a case of fakery in that sense, in a good sense. We will see many other cases where this same methodology will come into play, but what I wanted to here note today and then conclude is that I mentioned that after we discussed isolation protection, that this is the basis, this underlies all of this very popular today virtualization technology. By this we mean, for example, running Linux over Windows and vice versa, etc., etc. This is what virtualization, if you don't attach anything else, today is popularly being referred to. So, for example, in Windows 10, we have the Windows subsystem for Linux version 2 that came out, and that allows you to run actual Linux. So this is true Linux kernel code. For example, the latest Ubuntu, you can run over Windows directly using this technology, which is based upon what we discussed, isolation protection. And as I noted, we cannot discuss the technical details here beyond what we discussed to go here because we just don't have time to do that in this particular course. However, I wanted to give a sense of that you have much of the technical basis needed to actually understand what this means, how this actually can be made to happen. And for that, you just have to realize the following. A process is now is given the illusion of owning the CPU. And we call in computer science this thing formally, a process is a virtual machine because it owns the CPU, so it might as well be its own hardware. Now, all code in operating systems, all code is run by someone, by a process. So all code except at the initial bootstrapping phase is executed by a process, always. That's why we also have the null process, as we discussed. So when we are in, so here's our drawing, user mode, kernel mode, and here we have suppose two processes, P1, P2. To context switch to schedule from this guy to that guy means that we are now going to run this guy's code either in user mode or in kernel mode, upper half, lower half, and then we are ceasing to run this code and then running this code. So the CPU that's being shared is being occupied by different occupants, P1, P2, under the governance of scheduling with context switching under the substrate of isolation protection. So that's something that we all now know. Now going to this thing. You want to run Linux, say this version, you want to run Unix, and you want to run Windows. And Linux is going to have hundreds of processes. Unix is going to have hundreds of processes. Windows is going to have hundreds of processes over the same shared CPU. That's the virtualization environment that we are trying to understand. So how is that possible that over the same CPU you can run at the same time 3 separate operating systems, and if you can do that, then all other combinations are easily doable too. So how is it possible that you can run 3 operating systems at the same time over the same hardware, over the same CPU? Whether you run this guy, this guy, this guy, the CPU is being shared by processes. This guy, this guy, this guy. It's always a process that runs. A process that's making system calls, or a process that's running interrupt handling code in the lower half that might be part of Linux or some version of Unix or some version of Windows. But it's always a process that's running code in user mode, kernel mode, in kernel mode, upper half, lower half. So from the CPU's perspective, it's only changing its occupant from a process to another process to another process. If it's this process, it just happens to be that it's going to be running under Unix, which means interrupt handling will be done by the Unix's lower half code of the kernel. If this guy happens to be in the midst of making a system call, this process is running, but running code inside the upper half of this Unix version. Same for Linux, same for Windows. So all that has to here happen is that you add another operating system, typically called a hypervisor, that is then performing in essence context switching and scheduling of processes that happen to be running under Linux, under Unix, under Windows. But all that this guy is essentially doing is still scheduling and context switching of the shared CPU, with this guy now being attached to code that is part of Linux, this guy Unix, this guy Windows, but they're still running processes. And what this guy is doing is making the CPU being shared by multiple processes. The added complication comes in when you have Ethernet card through which packets are being received and packets are being sent out. Each of these guys thinks that they own this Ethernet card. Obviously, this is being shared by 3 operating systems at the same time. So this guy's responsibility now is to make sure that all these interfaces that it supports are again virtualized. So this guy's job is to give each of these guys the illusion that they own this Ethernet interface, when in fact they are all sharing them. So again, you have to virtualize resources such as interfaces. That's the additional complications that one has to drag in. And lastly, all of this has to go on very fast. It cannot be sluggish and slow. So again, speed is of utmost concern. If you do this and it just slows things down too much, then it's not going to be very useful. So how to make all of this work and go fast and be correct? That's the deep technical challenge that comes into play, but over half of it, maybe 70% of what goes into this, you have already learned by understanding isolation protection. More than that means we actually have to jump into the topic and then see what's going on. So we will stop here with that, but hopefully you'll get a sense, hopefully a big picture sense, that in virtualization, where you're running in general multiple operating systems at the same time, concurrently, over the same hardware, under the supervision of some other operating system, that this is really in principle doable, because this is being shared ultimately by processes, whether they run under Linux or Unix or Windows. It's still at the end of the day processes that are running, and as long as those things can be separated well, etc., the details which we are not going to go into here, it's not a big deal. It's doable. And all of this is doable because of isolation protection that builds a barrier around these processes, that builds a barrier around all these operating systems. And then what we just discussed, context switching and scheduling, which gives the illusion that every process running under Linux, Unix, or Windows, it doesn't matter. We are able to give them the illusion that they own the resource. So this plus this allows this to happen, which is very, very popular today. So let's stop here.